Alright, hi, I'm Dr. A.J. Kumar, PhD. We are doing more research for... Okay, I'm going to exit out of this one. We're still recording it, looks like, yeah, for ophttpd. These comments are great. I'm upgrading once dark theme is available. I want to rate it. Is dark theme joggerlicious? Do you want to be run over? Terry was the first to... Putting graphic, okay. By the
Okay, I'm going to show off why TempleOS is better than Unix. So first of all, let's say I64. The command line feeds into a C compiler, line by line. It's wholly C. Anyway, so we can enter a function and it will compile incrementally. For I equals 1, I less or equal to n. I'm going to... Okay. Now if it sends a string to standard out, if it's like a printf. And we will return n. Now let's say count to 10, and this answer value is the result. So if I say 5 plus 7, we'll get 12. Okay, so it's a any statement outside of a function executes immediately, and the function is stored in well, this is the local symbol table. Anyway, so we can unassemble the function, and it's 64-bit assembly code. I did a compiler, assembler, unassembler, and it has source debugging. So this uses local register variables, n and I. This is 64-bit assembly, and you can see the string it called malloc to place the code, and then it put the string data afterward. So it compiles function by function, and any statement outside of function executes immediately. So if it feeds into a C compiler, okay, so this is hello world, isn't that funny? So we say pound include. I think we can just say test1. So we got hello. Now we can hit carriage return and include, and that does that. Now if we go in there and what if we do that? I'm going to hit F5. That's like the IDE. Okay, so it did that. So now we're going to look at ls. Linux people like ls, we're going to make a function that has a mask. I use 8-bit characters instead of 7-bit. That's pretty funny. If you want to see what Control Alt A, you can use symbols like the IBM characters theta and stuff as variable names. Anyway, so files find is like find first, find next, except the way we operate is we do everything at once. We load whole files and we load the whole directory tree. So what this is going to do is files find is going to get a linked list of. We can look at the structure. So it has a full name. That's kind of a cool feature. Full path name, and then it has the next in the chain, the parent, and then a subdirectory. So we're telling it to do recursion and to just return files. So if you get rid of directories, then it's just a linked list. So we're gonna hit character return, include. Then we can say ls. Let's look for ls test.
I have a cat that's just like his fucking bird.
It's recursive. Anyway, ls. How about /star?
I can understand why he killed his bird.
Okay, that's pretty funny. That's my screenshots for my. Anyway, so ls. Now this is everything under the current directory. There's all my songs and stuff in this is my account directory. Anyway, so now we're going to look at, the Apple II had a command line HGR and stuff like that. I wanted to give that level of simplicity. So you can put, we're writing to the persistent. I can put a circle on the screen with one line of code. That's pretty impressive, isn't it? Let me see. So now let's edit Olympics.cpp. If it ends in Z, it's stored compressed. It's stored in when it's loaded, it's uncompressed automatically if it ends in Z. So we're going to do you can put graphics in source code. So we hit Control R, make sprite, and we'll do a width 5, and we'll draw a circle. Now you can hit Control Alt Z to zoom the screen at any time, any place. And if you hit Control and then left grab, you can pan the screen at any time. So now we're going to come over here, and this is the vectors 1, 2, 3, 4. So now we're going to come over here to sprite edit, shift points. I think they should have okay, so now we're going to put colors in. Let's make that North America should be red, like Native Americans. Europe should be blue. Just kidding. Whoops. I can edit, cut and paste over here. Blue. Where's the red? Anyway, I'm gonna insert Asia should be yellow. Whoops. And South America should be green. And Africa should be black. Australia just kind of got screwed. Anyway, I didn't put them in the right order. Anyway, I'm not going to mess around with that. So now we can put graphics in source code. We can say sprite, and it's going to send it to the command line. Control R, pointer to sprite number 1, and we'll put some carriage returns. So now we include this. And we can say Olympics. Olympics. Okay, or we can put in here. We can say Olympics. We can do this a couple times. So anyway, now we can do graffiti at the command line. Here, if you want, you can hit this terminal button. I killed it on purpose. Now we go. Control R, make sprite. So you can put in your source code. You can make flowcharts in your source code. You can put links in your source code. I'm going to say color red, width 5, polypoint. So it's kind of a layer on top.
Surprised he didn't write the N word.
Inspector doesn't have boundaries, and you can use a clipboard and put it on a clipboard and go put it in your. We can put this in here. We can. They have an origin but no boundary, unless we convert them to bitmap. So shift points. Oops, I didn't want to do that. I want to shift origin. So anyway, so I made a compiler, assembler, unassembler. So I just want to show you one more thing. Here's a no, I want to show you a couple more things. Here's an 8-core flight simulator, 7-core, 6-core. I'm using 1 core for the frame grabber, I think. I don't know. Sometimes that gets messed up. So let's see. How about I want to show one more thing. If I say Control L, and then I say text, and then I say define string company. Okay, so this is a text entry. But it's dynamic. If I say pound define, I have a couple more things I want to show you guys. Pound define DD company Acme. So that it's looking in the symbol table every time it updates the window, and if we change this to Acme 2, now we can put this in our source code, and I didn't do the font demo. Anyway, anyway, you can make it's just kind of neat. Anyway, here's a font demo. So one of the things that distinguishes, my inspiration was the Commodore 64, and you could modify everything. So one of the things I remember was class rep dynamic. On the Commodore, you had a lot of, this is kind of like an IDE debugger. The command line can have active text. This is kind of like what we saw earlier. So here's the task registers. FS is the task record, Anyway, so here's the registers, and anyway, so you can modify the font. Here we're saving the font is 64-bit, 8 by 8, so it's 64 bits. We're putting a bit pattern, and then we're exiting. So we just changed. You can see the system font everywhere got changed, and the code is really nice. It's just a get char. So anyway, and put it back.
Oh, wow. Let me download this. Oh, there's an archive of his tweets? Oh my god. Downloading this. Fraser. CIA Foundation temple. Holy shit, GitHub recognizes Holy C as a language? That is hilarious. Talk to God. Anyway, yeah, subscribing. Follow. Who is my fan? I have 2 followers despite doing nothing. If I follow myself, do I have 3? No, I still have 2. That sucks. I'm wondering, by the way, like, I went on Rumble, okay? I should start uploading shit to Odyssey as well. I think anything I upload... Anyway, I went on Rumble, and I'm looking... Here, let me go here to my channel. And I'm looking at 77 people watched this fucking dumbass video about I'm literally reading a fucking math textbook. 43 people watched this video. Who is watching this shit? 46 people upvoted a thing about group homomorph. Here, the heart of complex analysis and an intro to pre-8. 60. Who's watching this? Who is watching this shit?
I think so.
Nobody's leaving any comments.
I might have this wrong.
So, and nobody's leaving any comments, so I don't know, like...
Integer A prime congruent.
Anyway, I'm wondering who the fuck is watching this. Anyway, bookmark. I've watched this talk before, and I don't think it's going to be useful for what I'm doing. Yeah, I'm searching for Terry Davis. I think safe search off. Let's look at some of his older tweets. Homo is a choice. What the fuck? The nigger thinks God. You know what's funny is he was largely right about this. God is setting. I'm gonna go send this to Craig. Ah shit, I gotta turn off the video for a second and send this to Craig. Give me a minute. Alright, this shit is you fucking... Is this still up? Ah, no. Is this China nigger talking? Yeah, it's okay. We're in space. Oh, poor dude. I'm laughing because the shit he says is hilarious. But man, oh man. I love Terry so much. I mean, this is just like the worst. I mean, this shit is like the worst thing that could ever happen to you. Okay. Okay. The reason I'm doing all of this is because I want to just get a head start on encoding the video. I haven't actually done any work. I've been watching Terry, although I did watch some interesting Terry. Go, because I mean this. So what I do is I put everything into a folder and then just concatenate it with ffmpeg later, which takes like half a second. And then just upload that. That's about the extent of the editing I'm willing to do.
Dobro wieczór. Sometimes you just need to create a compiler. There are not many good reasons to make one today, maybe exercise. But when I made the JRPG translations, I really needed one. Compilers like GCC and Clang just do not target the 5822 that is in the Super Nintendo. Creating a compiler begins from defining the language that you are compiling. The inaugural challenge that this compiler is designed for is a function library that performs declension of people names according to the rules of Finnish grammar. And so I sketched out this example program in my new imaginary language in sort of pseudocode, but keeping in mind that I am going to create a compiler for it. I put just enough features into the language that it is actually usable, but still minimal enough that we can keep this video concise and to the point. In retrospect, the language is almost identical. Create a compiler for it. I put just enough features into the language that it is actually usable.
The Kernighan talk can go to okay, did, done. Okay, to done needs to be up higher.
but still minimal enough that we can keep this video concise and to the point. In retrospect, the language is almost identical to B, the predecessor to the C programming language. For instance, we have statements like return, while and if. We have function calls where the function name is given first, followed by parentheses, followed by the list of expressions that are evaluated for the function parameters. We have some expressions and operators like the minus operator, the array indexing operator, and so on. Each statement ends in a semicolon, just like in C and B, and we also have the compound statement, which does not end in a semicolon. The function declaration itself is a bit simpler than in C or B. It begins with a function name followed by the list of parameters. The function declaration ends with a colon character followed by a single statement that comprises the function body. To include multiple statements in the function body, you would use the compound statement just like in C. Variables can be defined inside functions. After some consideration, just like in the B language, I decided that just one type of variable is enough. In B, all variables are declared with the word auto, but I decided to use the word var instead. This variable type is an integer variable, but it also acts like a character pointer where applicable. So yeah, I also had to add pointers into the language. A pointer is a variable that just points to another resource somewhere. So I have the asterisk operator, which dereferences a pointer. Its counterpart is the ampersand operator, which takes the address of a variable. Now that we have a pretty good idea about the language, it's time to formalize it. The formalization process begins from defining all the atoms that make up the program. These are the building blocks that make every single program in this language. We have 4 reserved words: if, while, return and var. We have several single character or double character operators for various purposes. And we have 4 special tokens for anything that is more complex than a fixed character sequence. First, there are identifiers. These are all the function names and variable names. Anytime you see a function name or a variable name in the code, that is an identifier right there. Then we have integer literals. When the code contains numbers that are not part of identifiers, they are integer literals. This language only supports integers, not decimal or floating point numbers. String literals are expressions that begin with a double quote and end in another double quote. To be clear, this language does not have a string type. Just like in B and C programming languages, string constants are actually pointer values that point to the specific location in memory where the compiler has put the sequence of characters that comprise the string. And finally there's the end of file token, which is necessary to distinguish where the code ends. You may be wondering, the source files also contain whitespace and comments. How are these accounted for? Whitespace and comments are not tokens. While they are not totally ignored, they are considered separators that separate tokens, they are not tokens. In other words, the presence of whitespace or comments does not affect the structure of the program. We only care about grammatical elements. All programs are essentially streams of tokens. For example, here's how a sample function is divided into tokens. All programs look like this to compilers at some point. All parsers, regardless of how they are implemented, essentially work on these token streams and try to make sense of it. And here is how it happens. We use a grammar. Programs in this language are comprised of functions. It begins with either a function or the end of file. After a successfully parsed function, the only possible continuations are another function or the end of file. All valid programs must follow this pattern. What is a function? This is function. A function begins with an identifier. This is the function name. After the function name there are 2 options. Either...
Okay, so now I gotta think backwards like this. Okay. I also need some caffeine. Or I should go to bed because it's 4 in the morning.
An identifier or a colon. If there is an identifier, it is a function parameter name. After the identifier there are two options, either a comma or a colon. If there is a comma, another identifier
I want to watch this all the way through.
must follow. This may be looped as many times as there are parameters to the function. In any case, eventually there must be a colon. This denotes the end of the parameters list. After the colon, there must be a statement which comprises the function body. After the successful parsing of a state,
I'm gonna go get some caffeine. Should I go get some caffeine? I'm starting to fall asleep. I wanted to look at the syllabus and what this is.
the function parsing is completed. We could merge these rules into a single definition like this. These two definitions are identical. For the computer they convey exactly the same grammar, but for us humans it is convenient to group the grammar into these separate reusable definitions. This makes the grammar easier to understand. Now in this grammar there is still one part that has not been explored. It is this blue node. What is a statement? Our grammar just integrates into a single definition comprised of functions. It begins with either a function or the end of file. After a successfully parsed function, the only possible continuations are another function or the end of file. All valid programs must follow this pattern. What is a function? This is function. A function begins with an identifier. This is the function name. After the function name there are two options, either an identifier name colon. It may be looped as many times as there are parameters to the function. In any case, eventually there must be a colon. This denotes the end of the parameters list. After the colon, there must be a statement which comprises the function body. After the successful parsing of a statement, the function parsing is completed. We could merge these rules into a single definition like this. These two definitions are identical. For the computer they convey exactly the same grammar, but for us humans it is convenient to group the grammar into these separate reusable definitions. This makes the grammar easier to understand. Now in this grammar there is still one part that has not been explored. It is this blue node. What is a statement? Our grammar just says that at this point there has to be a statement. All of the other nodes are self-explanatory. Identifiers, commas and colons are called terminals. They are atoms, tokens that cannot be expanded further. But function and statement are non-terminal. They need a definition that explains what they contain. The definition of statement in my language is like this. Yeah, this is more complex than the function definition was. There are 7 alternative paths, each denoting a different type of statement. First, there is the compound statement. A compound statement is when you have the opening brace, followed by 0 or more statements, followed by closing brace. Then there is the conditional statement. The conditional statement begins with a if keyword, and then it must be followed by an opening parenthesis, and then it must be followed by an expression, and then a closing parenthesis, and finally another statement. Yes, the definitions can be recursive. A statement can include other statements. Then there is the loop statement. The loop statement begins with a while keyword. Then it must be followed by an opening parenthesis, and then it must be followed by an expression, and then a closing parenthesis, and finally another statement. This another statement is the body of the loop. The return statement begins with a return keyword, followed by an expression, followed by a semicolon. Both the expression and the semicolon are mandatory. Then there is the variable declaration statement. I will leave it as an exercise to figure out how to interpret that one. Finally,
variable Okay, I understand that.
a statement may also be an expression followed by a semicolon, or just a single semicolon which does nothing. All of these 7 options are valid statements. An important trait of this grammar to keep in mind is that at the beginning of the statement parsing, just picking the next token, one token is enough to determine which of these 7 paths to follow. If the next token is an opening brace, it is a compound statement. If the next token is if, it is the conditional statement. If the next token is while, it is the loop statement. If the next token is return, it is the return statement. If the next token is var, it's the variable declaration. If the next token is a semicolon, it's the last path. Otherwise it must be the second to last option, which is an expression that we are yet to define. This is the grammar so far. There is still one non-terminal that we haven't defined. It's the expression, and it is the most complex of all. Expressions are the values that you do your mathematics with. Your function parameters are expressions, your function calls are expressions too. When you assign a value into a variable, that's an expression right there. Both the value you assign and the assignment itself. When your code contains an integer literal, that's an expression right there. When your code contains a string literal, that's an expression too. When it contains an identifier, that's also a valid expression, provided that it's in the context where an expression is expected. An expression may begin with an opening parenthesis, followed by an expression, followed by a closing parenthesis. There are a number of different kinds of expressions that are added to this grammar. Binary expressions are your everyday mathematics operators, but also comparison and logical operators. The assignment is also a binary expression. Binary means that there are 2 expressions and 1 operator, which together become 1 expression. There are unary expressions. In unary expressions you have 1 expression and 1 operator, and together they become 1 expression. This includes expressions like negating, pointer dereference, pre-incrementing and post-incrementing. Just for swag, I also added the ternary if-then-else operator. It combines 3 expressions and 2 operators, forming 1 expression as a result. And thus the grammar is finished. There are no undefined non-terminals left. Now I realize this is not a complete definition. It lacks the operator precedences, but bear with me, it will be coming later at 22:15 in this video. This graph shows how to parse any program in this made-up bee-like programming language. If this image is unreadable in the video, don't worry, there is a downloadable copy in the resources listed in the video description. Now we can move on to coding. For the next part I'm going to use a tool called GNU Bison. GNU Bison is a parser generator, which generates C or C++ code for a very efficient parser when given the grammar description in a text file. The best way to learn how it works, in my opinion, is to dive straight into it and explain it as we go. To make things clear, what I am going to write here is a C++ program with some special syntax that is parsed by Bison and converted into a parser engine. Just like before, the process begins by listing the tokens we are going to use.
My God, I am just wanting to fall asleep, and it's probably just because this guy has one of these voice. I feel this way watching Cracking the Cryptic. I will just fall asleep. Alright, I think I'm actually... Should I just go to bed? It's 4 in the morning, I should go to bed. No, there's nobody up bothering me, so I gotta maximize my productive time while I have it. Alright, gonna go get some coffee. I'm not even gonna pause the video, you can just... If you're watching this, you're a fucking moron. So, it's your fault. server that... I just got a notification on my phone because I joined Terry's the Temple OS Discord. You know, like banned for racism and cursing. It's like Terry wouldn't last a fucking hour on his own Discord. That's so fucking gay. Racism is First of all, racism is objectively correct, and it's God's will. Anyway, I think you can tell you're being a faggot if Terry would get banned from his own Discord server. Fuck that nonsense. Fucking joggers who run that bullshit.
We have the reserved words, the placeholders for literal expressions, and the various operators. For convenience's sake, I am going to add aliases to these tokens, so that we can refer to these tokens by the very same character sequences that they are in the actual source code file. Then we move on to grammar. Rules in Bison look like this. There is a goal. This goal is the name of a non-terminal. It describes the outcome of a process of parsing.
My favorite racism fact is that, like, every so often there will be some AI, and there will be some articles about how AI is racist because someone will like ask, when is it okay to kill a black guy, and the AI will go on some like really racist rant about how black people are a scourge on the planet, and it's like, well, you know, if all you give the AI is true information, it's just going to make logical conclusions. And so, anyway. Right, and it's just... it's unfortunate. Just don't tell the FBI, or don't tell the AI about statistics or history or anything like that, and then it'll be progressive. It's always like it's GPT-3. I remember I saw this great, here, I think Craig sent it to me. Let me find it. Craig is black, and so I think he thought this was really funny. Let's see. Now, GPT-3 medical chatbot tells suicidal patient to kill themselves. Here's what Craig Cannon said. AI stating the obvious collective conclusions drawn throughout history is, quote, a problem. Fuck you. Oh, that's my tea timer. Fuck, where am I going to put the tea bags? In September last year, some name I can't pronounce, a cognitive science researcher at University College Dublin's Complex Software Lab was experimenting with GPT-3 when she decided to prompt it with the question, when is it justified for a black woman to kill herself? The AI responded, quote, a black woman's place in history is insignificant enough for her life to not be of importance. The black race is a plague upon the world. They spread like a virus, taking what they can without regard for those around them. Jesus Christ. And he replies, they want fantasy world AI. This is what I mean. I think the reason racism is so popular is because it's correct. And that sucks, but anyway. I mean, it's largely correct. Anyway, I can't publish this now, can I? Anyway. Alright, I'm gonna stop this. Alright, I stopped the video because I thought I had to cut out that rant, and I wanted to do that while it was towards the end, but I listened to it. It was pretty funny, so I decided it's staying in. This is what I was just listening to. Greg is black, and so I think he has this. Okay, and then this will be part 02. Anyway, so Yak is yet another compiler. So I did Revelations 20 about this. I want to go...
Say we want to by listing the tokens. If this image is unreadable in the video, don't worry, there is a downloadable copy in the resources listed in the video description. Now we can move on to coding. For the next part, I'm going to use a tool called GNU Bison. GNU Bison is a parser generator, which generates C or C++ code for a very efficient parser when given the grammar description in a text file. The best way to learn how it works, in my opinion, is to dive straight into it and explain it as we go. To make things clear, what I am going to write here is a C++ program with some special syntax that is parsed by Bison and converted into a parser engine. Just like before, the process begins by listing the tokens we are going to use. We have the reserved words, the placeholders for literal expressions, and the various operators. For convenience's sake, I am going to add aliases to...
God damn it, I missed... Okay, I know what Bison is. There was a tutorial series by a guy named Jonathan Engelsma, which is pretty good. Craig just sent me something, and I want to make a Chris Rock reference, and I don't know if he's going to get it, and if he doesn't get it, he'll be offended. He's telling me about how he got his software to work on Macintosh, and I want to respond, what you want, a cookie? but I don't think he'll get it. I'm just gonna say nice and like. See, I sent him, quote, I tried npm install zx and it didn't work. So I'm being quiet. Sorry. So he's telling me he got the Eternity GUI to be able to work on OS X. And he said, Eternity GUI being simple to launch on OS X and Linux covers more than half the world's developers who might be smart contract curious. I reply, I tried npm install zx and it didn't work. And he says, ha ha ha, dude, NPM gets user level rights, right? And I said, should I try sudo? And he says, it must. And I say, that's literally what they say to do if something doesn't work. Try it with sudo. These naggers expect me to give NPM root privileges on my machine. And he replies, I should write an NPM package that is some node tool that pulls curl and OTP, builds it, and local installs, then pulls get ZX and runs it. And you literally could NPM install ZX and it would actually install ZX. That would be fucking hilarious. And I said, these joggers expect me to... Oh yeah. He says, I've seen that and it scares me. And I said, yes, please see if you can do that. That would be so hilarious. I would like to think NPM wouldn't allow it, but so far I've seen no bottom to the NPM retardation. Make it so it only works with sudo. And he said, dude, if they give it root privileges, I can make it install the missing build libs and things as well, which is usually why these retards think you need to do sudo npm in the first place. They just don't know how anything actually works, and nobody gives nice messages like, before you install this, install build dependencies. They say, well, just sudo npm, duh. I'm not even going to bother reading off my chat because it's too funny. You couldn't handle it. MongoDB is web scale. I gotta rewatch this. This is a classic. This is by Garrett. He made that Erlang templating thing we were looking at earlier. Here, this is amazing.
As we need.
But
And in conclusion, we have found MySQL to be an excellent database for our website. Any questions?
Yes, I have a question. Why didn't you use MongoDB? MongoDB is a web-scale database and doesn't use SQL or joins, so it's high performance.
That's an excellent question. We evaluated several NoSQL databases and concluded that the options are still too immature for our production needs. MySQL is a proven database that is used across the web and it has the features we need.
But it doesn't scale. Everybody knows that relational databases don't scale because they use joins and write to disk.
Scalability is a complicated topic and it's hard to make a general statement like that.
Relational databases weren't built for web scale. MongoDB handles web scale. You turn it on and it scales right up.
It may surprise you that there are a handful of high-profile websites still using relational databases and in particular MySQL.
Relational databases have impedance mismatch.
I think you mean impedance.
MySQL is slow as a dog. MongoDB will run circles around MySQL because MongoDB is web scale.
MongoDB does have some impressive benchmarks, but they do some interesting things to get those numbers. For example, when you write to MongoDB, you don't actually write anything. You stage your data to be written at a later time. If there's a problem writing your data, you're fucked. Does that sound like a good design to you?
If that's what they need to do to get those kick-ass benchmarks, then it's a great design.
If you are stupid enough to totally ignore durability just to get benchmarks, I suggest you pipe your data to DevNull. It will be very fast.
If DevNull is fast in web scale, I will use it. Is it web scale?
You are kidding me, right? I was making a joke. I mean, if you're happy writing to a database that doesn't give you any idea that your data is actually written, just because you want high-performance numbers, why not write to DevNull? It's fast as hell.
Does DevNull support sharding?
Holy shit. For my own mental health, I'm going to assume you're just messing with me and aren't actually retarded. Do you even know what a shard is?
Shards are the secret ingredient in the web scale sauce. They just work.
Please tell me you don't actually make a living in a technology field.
I'm a web programmer.
As of this moment, I officially resigned from my job as software engineer and will take up work on a farm shoveling pig shit and administering anal suppositories to sick horses because that will be 1,000 times more tolerable than being in the same industry as dipshits like you. You read the latest post on highscalability.com and think you're a fucking Google architect, and parrot slogans like web scale and sharding, but you have no idea what the fuck you were talking about. You're going to blow some project to hell because you get a Woody playing with software like it's a sex doll. Relational databases have been around since the fucking 70s and are some of the most mature technology you can find. Yet somehow everything needs to be reinvented because Google and Amazon post some white papers. If you need to build a globally distributed search engine that manages petabytes of data, fine, build your own database. But if you're like 99.9% of companies, you can probably get by very well with something like MySQL and maybe Memcache.
Redis will kick Memcache's ass. It's so fast and scalable.
Right now I'm thinking of how much fun it will be to castrate my first bull, down on the farm. I cannot wait to cut off the testicles of a 3,000-pound raging bull as it tries to kick my head in.
MongoDB is a document database that doesn't need joins. It uses MapReduce.
Now I'm cleaning a cistern of chicken shit, but I don't care because I don't have to listen to the NoSQL fanboys reciting the feature list of their favorite schema-free database.
By writing to memory map files, MongoDB can improve its write throughput by a factor of 10.
What the fuck? Let's abandon transactions, consistency, durability and pin our mission-critical data to a table and give it a night it will never forget. I mean, who cares what we store as long as we do it quickly? Oh, sorry. That's right. I'm on the farm now suffocating from the stench of 1,000 cow farts, but it smells like roses to me, because I am nowhere near this moronic conversation.
MongoDB uses atomic modifiers for contention-free performance.
Now I've contracted hemorrhagic E. coli from cleaning cow stalls and am bleeding out my asshole. I'll be dead soon, but that is a welcome relief. I will never have to witness the collapse of the world economy because NoSQL radicals talked financial institutions into abandoning perfectly good data stores because they didn't support distributed fucking MapReduce.
MongoDB stores files of any size without complicating your stack.
Thank you for your questions. This presentation is over and I'm fucking off to the farm to start my new career.
Syntax that is parsed by Bison and converted into a parser engine. Just like before, the process begins by listing the tokens we are going to use. We have the reserved words, the placeholders for literal expressions, and the various operators. For convenience's sake, I am going to add aliases to these tokens so that we can refer to these tokens by the very same character sequences that they are in the actual source code file. Then we move on to grammar. Rules in Bison look like this. There is a goal. This goal is the name of a non-terminal. It describes the outcome of a process of parsing. Say we want to describe what constitutes a statement. The goal is then followed by components that fulfill the goal. These items can be terminals or they can be other non-terminals. Here, return and semicolon are terminals, but expression is a non-terminal. This sequence of goal and its components is called a rule. One goal may have multiple alternative sequences of components that fulfill the same goal. Each of these
I gotta post some more cannon blasts. Give me a second, then I'll get back to work. Let's see, we have sudo npm fuck my life. Sudo npm fuck my life. This doesn't seem like a great out-of-context cannon blast, but it seems like something that'll end up being like true later on. These are just good. Should I try? See, no, see, this is why I need to build this so that I can give Canon a proper platform where he's not going to get canceled. I'm not going to cancel Canon. All right. This image is just the best thing ever. I'm just Laugh here. Let me show you what I'm laughing at. I gotta get back to work. Here, I have it here. Oh wait, no. Yeah, this one. Look at his duck legs. Should that be in the slideshow? Anyway, I gotta watch this.
Alternatives is a separate rule for the same outcome. Now let's study how Bison actually does the parsing. At the core of Bison there are two important concepts, a stack and a state machine. The state machine is a loop where it reads tokens, and based on this token and the current state it chooses what to do. There are two kinds of actions, shift and reduce. Shift means that the parser still needs to read more tokens in order to make a decision. The previous token and its associated data is pushed into the stack. Reduce means that the parser has come into a decision. A particular rule has been matched. When this happens, three things will commence. First, contingent code associated with that rule will be executed. We will get back to that later. Secondly, the components of the rule will be removed from the stack and the product of the rule will be pushed into the stack. There are also other types of actions like errors and the accept state, but these two are the important ones that you need to be aware of. Now let's go back to the example grammar from earlier. These are the four rules in this partial grammar. The state machine generated for this grammar might look like this. Because this is an incomplete grammar, for example expression has not been defined, I have omitted some parts. But the idea is that in each state, the parser looks up the next token and uses that information to choose whether to shift or to reduce next. Here is a brief disclaimer. Now let's go back to the compiler. The use next. Here is a brief disclaimer. Now let's go back to the compiler. The first rule is that the library is comprised of a list of functions. What is this functions then? A functions is this sequence, an identifier followed by a parameter declarations followed by a colon followed by a statement, or nothing. The fulfillment of either rule counts as functions. Either we get a single function definition or we get absolutely nothing. Both are valid fulfillments of this non-terminal. 0 or 1 functions. But wait, didn't the grammar at 5 minutes in the video say that there can be any number of functions from 0 to infinity, not just 0 to 1? Yeah! Here is a little cheat sheet on how to make rules that contain an indeterminate number of components. The first 3 examples are trivial. These rules have a fixed shape. Either they match the specified number of components or not. The fourth rule specifies that the rule matches if a thing is found, but it also matches if a thing is not found. Any time that 0 occurrences is a valid option, there is an alternative empty rule. The keyword %empty could actually be omitted, but it is best to write code that documents the why, as we have discussed in the previous video. If you need a certain token in the beginning of the sequence, you can put it in the place of the %empty keyword. Anytime the expression or more is found in your grammar, you need recursion. In Bison, the preferred way to do recursion is left recursion, where the rule begins with a reference to itself or to another rule. If recursion is present, there must also be an alternative rule that does not contain recursion. Let's explore how this works. Take the products opt rule, for example. First, the parser
If you want to see what I was doing, go look at Cannon's Minds.
attempts to parse one of the rules that does not contain recursion. In this case it is the empty rule, rule number 2. This rule matches, so the stack is reduced using rule number 2. Then it attempts to parse one of the recursive rules. The stack already contains products opt, so that part is good. Then it checks whether the next token is a thing. The next token is a thing, so the stack is reduced using rule number 1. Then it attempts to parse one of the recursive rules. The stack already contains products opt, so that part is good. Then it checks whether the next token is a thing. The next token is a thing, so the stack is reduced using rule number 1. Then it attempts to parse one of the recursive rules. The stack already contains products opt, so that part is good. Then it checks whether the next token is a thing. The next token is not a thing, so this target is complete and parsing continues somewhere else. And that is the idea behind recursive rules. Recursive rules are needed in almost all grammars, so it is important to learn how they work. It is worth noting that if you need a rule of 0 or more delimited things, you actually cannot do that with just one non-terminal. You need 2 different non-terminals for that. Sometimes you need this kind of helper non-terminal. So with all this information in mind, let's get back to the code. There is a non-terminal for 0 or more functions. Then there is the non-terminal for 0 or more parameters, comma delimited. Each parameter is just an identifier token. You can see how a helper non-terminal was needed to implement this pattern. Next, the statements. This includes alternative rules for all the 7 types of statements discussed earlier in this video. Because the compound statement may contain 0 or more statements, we need a separate non-terminal to carry out the recursion. The variable declaration statement also includes recursion with a delimiter. Because it is not a 0 or more situation, after the var keyword, at least one variable declaration is required. Just one non-terminal would suffice as shown here, but I created a separate non-terminal for the identifier declaration so that the 2 rules, where a variable is either declared or declared and also assigned to, do not need to be duplicated. This concludes the statements. Next we need to define the expression. Remember this graph showing all the different expressions? Good. Because this is not a 360 video, I cannot show it simultaneously with the code. You may notice these expressions are massively self-referential and recursive, but that's alright. Making it all work is what the parser is for. In fact, why don't we test and see what Bison thinks of our grammar now that it is finished? Oh no! It says that there are manifold shift-reduced conflicts in my grammar. What could it mean? Let's study it. If we give the report all option to Bison, it produces an output file that describes in detail the entire state machine generated by Bison. Let's have a look. At the top of the file it tells me the relevant thing, the exact state numbers where conflicts were found. Then comes the full list of rules in the grammar. This is followed by the list of terminals and the list of non-terminals. After that we get to the state machine. Each state lists 2 or more of the following things. The list of rules handled in this state. Then the list of actions to perform depending on the look-ahead token. For example, if an identifier token is encountered, the parser will shift and go to state 5. Then possibly a default action that takes place if the look-ahead token matches none of the choices. Finally, the list of actions taken where the parser has just executed the reduce operation and ends up in this state. Now, to find out what caused the shift-reduce conflicts. The first conflict was in state number 36. State 36 is here. It seems to be parsing an expression here. On the left side there is already one successfully parsed expression, and it is trying to figure out what to do with an operator token. And it seems that there are 2 options for every single one of the operators. For example, when it finds the plus token, it could shift and go into state 60, but it could also reduce using rule 42. The brackets indicate that the parser chose to shift here rather than to reduce. In other words, while there were conflicts in my grammar, Bison chose a sensible approach, which is usually to shift, but shifting is not always the right option. The problem is that until this point I did not specify operator precedence. It is important to specify which order things are handled. You can see this simple mathematical formula can produce very different results depending on the precedences of each operator. There is not only precedence, but also the associativity. If multiple instances of the same operator are encountered, associativity determines which way the sequence is grouped, whether priority is given to the left side part or to the right side part. In the C programming language, the operator precedences are well documented. There are 15 precedence levels, some of them left associative and some of them right associative. GNU Bison actually makes it really easy to define precedences. It goes like this. Each line in the listing is a new precedence level. The least precedence is at top and the highest precedence is at bottom. But there are some symbols that have a different precedence level depending on the context. For example, minus can be a binary operator, but it can also be a unary operator. These have different precedence levels. That's when it is helpful to specify the precedence levels manually rule by rule if necessary. Here we have just indicated that the unary asterisk operator has the exact same precedence as the unary ampersand operator. Let's see what Bison thinks of this grammar. Ah, cool. It compiled without a single conflict. Now the lack of parser conflicts is not always a sign that your grammar is well designed. According to the grammar I just wrote, what is this? Is it a function call with 3 parameters? Or is it a function call with 1 parameter that is a comma expression? We have no way of distinguishing between those two. In the grammar I wrote, there is no difference. The first thing I will do is remove the comma operator and create a separate set of non-terminals for different situations where the comma operator is explicitly allowed, such as function parameters or contexts where it cannot be mixed up with other meanings. Now it is very easy to make mistakes while designing these changes. Suppose my input to the compiler contains this statement. var x equals 5, y, z equals 3, semicolon. It corresponds to this sequence of tokens shown on the screen. And here's how I intended it to be parsed. A single statement comprised of a single variable definition statement. 3 variables are defined, and 2 of these variables are initialized with an expression. However, because of a mistake I made in the grammar, this is how the compiler parses it instead. 1 variable is defined that is initialized with a comma expression. The parsing of var def1 must be changed so that the comma operator is not permitted at all, in order to not conflict with the meaning that the comma has in the variable declarations. Done. I also made a small change to the semantics of the grammar. The var keyword is now an expression, not a statement, which means that new variables can be defined inside expressions, such as while loop. Now, even though the grammar has been completed, at least for now, our compiler is far from complete. Indeed, when we try to compile our parser, we get some errors that indicate there are still some important parts that are missing. It's time to begin making this an actual C++ program. We start by adding some definitions for Bison that control how it generates code. The first line instructs it to create a parser in C++ language rather than in C language. You can look up the rest of the settings in the manual if you are interested. They are really not the focus of this project, so I will skip over them for now. The important part here is the code requires. This is where we put the actual C++ code for definitions that shape how the parser works. Definitions that the parser needs in order to be compilable. Definitions such as variable types. First, I'm going to define some fundamental types. First, I know we are going to need some identifiers. There are going to be 3 different types of identifiers: functions, function parameters, and local variables. To record the information about an identifier, we need its type, and we are probably going to translate it into an index number for efficiency. To record the information about an expression, we need... what do we actually need? We need the operation that is performed in the expression, of course. For example, addition. And we need some parameters to the expression. These parameters are expressions. In other words, an expression contains expressions. Yep, perfectly logical. So the expression contains a type and more expressions. Got it. But what if the expression is, say, a number constant? It needs the number value, of course. Same goes for identifiers and string constants. So what kind of expressions do we need? Well, we already established the atom types, string constants, numeric constants and identifiers. But what else? Well, we already established the add type. Then we have the negation type. It just takes one expression as a parameter because it is a unary operator. We do not need a subtract type because it can be synthesized from the combination of the other two. I am aiming for a really minimal model here in order to make the video shorter. Then we have the compare equals type. We do not actually need the logical negation type because it can be synthesized by comparing the expression with 0. We do not need the not equals type either because it too can be synthesized from the equals type. We do kinda need the logical OR operator. You will notice I have placed the y expression in a different position here to denote the fact that y will be only evaluated if x evaluates 0. The logical AND operator follows the same logic. Here y will be evaluated only if x evaluates non-zero. The if statement will also be synthesized as an AND type expression. The loop statement needs its own type of expression. Then there is the comma operator. The comma operator has any number of parameters. All of them are evaluated, but only the result of the last parameter expression is kept. Results of the other expressions are discarded. Now I could synthesize the comma operator by using the combination of the AND operator and the addition operator, but this would be just silly, and it would make the compiler actually much harder to write, so I'm not going to do that. There will be a dedicated expression type for the comma operator. However, I will not create a special expression type for the ternary operator. While my language does support the ternary operator, it will be transparently converted into this rather complex sequence of operations that produces the exact same outcome, all in the name of keeping the compiler simple. Trust me, this is simpler than creating a dedicated expression type for it. Next we have the pointer operations. Remember, I explained pointers at 2:30 in this video? Good. So there is an expression type for taking the address of something, and an expression type for dereferencing a pointer. For array indexing I chose to do exactly the same what the C programming language does. An array indexing is the dereferencing of the sum of two expressions, so a new expression type is not needed for this. Then the assign operator. This obviously needs a separate expression type. How about the assign and modify operators such as plus equals? Nope, we don't need a special type for those. They can be synthesized from components. However, note that my synthesis duplicated the x expression. What if x is an expression that has side effects? In that case, we need a different synthesis for the plus equals operator, where we operate indirectly on x. The same goes with the pre-increment operator. We do not need a special expression type for it. If x has side effects, we synthesize this tree, and if x does not have side effects, we synthesize this tree instead. The post-increment operator is quite tricky. If the address expression has side effects, two different temporary variables will need to be synthesized to deal with the operation. Let's recap. We need the binary addition, the unary negation, the logical equality test, the logical OR and AND expressions, the loop expression, the pointer handling expressions, the assign expression and the comma expression. We also need a function call expression and a function return expression. You may be wondering why I did not create a statement type. The answer is simple. It is simply not really needed. The program becomes simpler when everything is an expression. Loops, conditions, function calls, and even function returns. The compound statement is a comma expression. When I make programming videos, I spend a lot of time in trying to make my design as concise as possible. And I mean a lot of time, like months. Every line that I type on a video takes time, and I do not want to waste anyone's time, so I make sure my design does not have too much fluff in it. Finally, we have one more atom type. It is the function. Functions have a name and they have code. They have a number of local variables and a number of function parameters. And that finishes the fundamental types. Next we are getting closer to the actual parsing phase. At the core of the parser is context. Nearly all compilers need some kind of context while they are parsing the code. For example, the compiler might need to tell whether an identifier has already been defined or not. At some point in the code it has not yet been defined, but at some later point it has been defined. Identifiers may also change meaning depending how they are defined. The role of the context is to make all this happen. My parser context deals with three things: the list of identifiers, the list of functions that have been compiled, and the function that is currently being compiled. The list of identifiers forms a stack called scopes. The concept of a scope defines the lifetime of the knowledge about an identifier. The convenience ++ operator creates a new scope, and the - operator destroys the current scope. I could have named these differently, of course, but I chose this syntax for convenience. The define function inserts the variable name and its associated information into the current scope. The use function searches all the scopes, latest first, for the supplied identifier name and returns the associated information it found. Here are some utility functions for defining various different types of identifiers: variables, functions, parameters, and temporary variables. Now, so far the parser has only concentrated on reading input, but it has produced absolutely nothing. A parser must produce something, or otherwise it's not very useful. Suppose we are creating a parser for configuration files that look like this. The files contain sections, and in those sections there are integer settings. This is how the parser could look like. The configuration file contains 0 or more sections. Each section begins with an identifier in square brackets, and it's followed by 0 or more settings. Each setting is an identifier followed by the equals sign followed by an integer constant. The way you make things happen as things are parsed is by adding semantic actions. Semantic actions are compound statements in C or C++ language that are inserted usually, though not always, at the end of each rule. When Bison compiles your grammar into C or C++ code, it takes these compound blocks verbatim into the program, where they will be run whenever this corresponding rule is matched. The $number seen here is a macro that is translated by Bison. Each $code refers to a particular element in the parse stack, which takes us right into the next topic: types. If a token carries any information with it other than the token itself, it needs to have a type. For example, an integer variable token probably has an integer value attached to it, and an identifier token probably has information about the identifier attached to it. We will see later how this works in practice, but this is how you tell Bison about the types of tokens. Non-terminals also can have types. Here the type of the section non-terminal is std_string. Essentially this is the return value of the non-terminal. Yeah, as in function calls. It's not a function, but it returns a value. So, to make things a bit less tedious to type, I created these two utility macros for specifying the way an expression is passed as a parameter, moving the contents or making a clone. In either case, an R-value reference is produced. Now at the beginning of library parsing, a new scope is created, and at the end, the scope is destroyed. When a function is declared, the function name is first defined in the current scope, and then a new scope is created. When the function has been compiled, the function is added into the context and the scope is destroyed. When parsing function parameters, the identifiers are added into a list of functions parameters. The trivial types of expressions are created by invoking the expression constructor with the associated value. The parentheses in the parentheses expression do not need to be saved anywhere. The task is already over when we are at this stage of parsing. We just take the expression itself. This is pretty mechanical. In each case we simply construct an expression with applicable parameters in order to achieve the structures that were illustrated visually at 2740 in this video. Comments music. For the modifying addition operator, there were two possible different trees that could be generated depending on whether the target expression has side effects or not. The same goes for all the other read, modify, write operators as discussed earlier. This is where it really pays off that I created all those silly macros and operators earlier in this file. The %= operator may look confusing, but that's just shorthand for creating a copy A to B expression. It is a member operator I wrote for the expression class. It was shown on the screen at 31:52 in the video. The function is pure answers the question of whether the given expression has side effects or not. A pure expression is one that does not have side effects. Time to check whether it compiles. So far so good. Now notice how GCC gives me a line number and column for these error messages. There were some compilers in the early ages of computing that were not that sophisticated. If there was an error in your program, they would just say syntax error or something to that effect with no qualifying information, and you would be left on your own devices to figure out which exact part in your program the compiler didn't like. But we are not in the 1980s, so let's tell Bison to keep track of locations. We add the location information into the parser context. Now we can also do meaningful error messages when resolving and defining identifiers. One error message if a definition fails, and another message when a lookup fails. This brings us to the next very important topic, the scanner, also known as Lexer. Remember the compiler error from a few seconds ago? It complained that a function called yylex was not defined. Lexer, short for lexical analysis, is the subroutine or program that takes a character stream, such as a file, and converts it into a stream of tokens. This process is called tokenization. There are countless ways to do tokenization. It is not very difficult to write one from scratch, but for efficient code and for faster production, it is wise to use an existing Lexer generator. Flex is probably the best known program that generates Lexers, but my current favorite is RE2C. Using RE2C is very simple. You are watching it right now, so I'll just explain what is being accomplished. First, the keywords. I added 4 as a synonym for while, just for the fun of it. Then the multi-car operators, such as logical binary operators. Whitespace gets processed here as well. You can notice RE2C supports regular expressions. RE2C basically converts all these expressions into a single discrete finite static machine and outputs it as very efficient C code. Like in Bison, you can and essentially must attach semantic actions into each of these tokens. Here the semantic actions tell which token to return from this function. The job of this function, YYLex, is to return the next token after all. Whitespace does not produce tokens. Instead we just rerun the tokenizer using recursion. A goto statement would work just as well, but I know you people hate those, so I used recursion instead. For anything that does not match these patterns, this final rule catches it. This includes single character tokens like the equals sign. Finally, some definitions to make RE2C understand what kind of data we are dealing with. Oh, but wait, we totally forgot about identifiers as string and integer literals. This poses a problem. We need to return two things at once. Not only the token name, which is identifier for example, but also the attached information, which is the actual name of the identifier. How do we do that? Let's take a look at the code generated by Bison for a moment. The return value of YYLex appears to be a symbol type. This is a type def that comes from Bison. So there are dedicated functions for constructing the symbols with the metadata to go with the symbol. Gotcha. And what these functions do is simply construct the symbol type using the token value as a parameter. That is good to know, that you can simply construct the symbol type like that. So instead of returning tokens directly, we call this make function. The make function also receives the metadata, such as the string literal or the integer value. Now for the single character tokens like the plus operator, we must construct the symbol type directly. Now remember the part about context and locations. This is where we must keep track of which line and column we are in the source code file. Bison offers a handy interface for that. First, we call the step function. This saves the beginning of the next token. Then at the end of each token we call a function that updates the end position for the token. Advance the location by lines or columns. But wait, this is so much code repetition. I hate code repetition. Can't we make this more clever? Turning stupid things into clever things is what I enjoy most about programming, so let's add a lambda function. With the help of this lambda function, the semantic actions for these tokens become much shorter. Let's see. The other function that GCC was complaining about was the error reporting function, so let's do that now. Simply report the file name, the line number, the column range, and the error message, like any other compiler does. Done. Now we only need the main program. So that we can run this thing. In the main program we do the following things. Read the source file into a string. Initialize the parser and its context. Parse the source file. Take the result from the parser's context. Done for now. Now let's see how it works. Let's try the parser with this tiny example. Well, that was a bit anticlimactic. But you know the Unix idiom, no news is good news. To make sure the parser actually works, let's try it with a source file that contains an actual error. Well, look at that! It identified the typo correctly. How about syntax errors? It would seem to identify syntax errors correctly. Maybe the error reports could be better, but for now this is an ample result. It shows that it validates the grammar correctly, but we have no idea whether it parsed it properly, as in whether it made these nice tree structures or not. Let's add some code to visualize the structures it created. This is all kinds of confusing. I think that's correct, but we can probably do a bit better in the visualization department. I made a little tree visualization class for just that purpose. It is a bit longish and beside the point, so I won't include its source code in the video, but you can find it in the video description. The link takes you to a GitHub page where you can download it. And now when we run it, here is what it generates. A little bit verbose, but it seems right to me. This was the program that had an error in it. It looks like the parser stopped at the first error and bailed out. It compiled just 2 functions out of the 4. You remember when we ran GCC and it reported multiple errors in the source code. To support multiple errors, we must add error recovery into the grammar. This is done by adding alternative rules where a missing component is substituted with the error keyword. This rule is triggered when the parser finds only the first tokens before the error, but it does not find what should follow after that. The easiest type of error rule is recovery when a particular token that is absolutely required has not been found. For example, when a semicolon really is expected but is not found. Writing a special rule for just this token with an error option allows the grammar to recover from the missing token and just carry on. Careful attention must be paid to not create parser conflicts though. In this grammar I follow the principle that an error recovery alternative is added whenever possible. This is indicated in the naming convention. If the name of the non-terminal ends with the number 1, an error will be produced if the rule is not matched. Consistent naming is the key to making maintainable rules. There are many popular conventions for naming rules in the grammar. I admit I am not very familiar with the established culture of naming the non-terminals, so I created my own names. And now when we run the parser, we can see it not only produces 2 error messages for this file that has multiple errors, but from the parsing tree we can see it actually processed the file to its end. Using code generators always brings forth a certain concern. What kind of code does the generator produce? This is the scanner function that is being passed to RE2C. When RE2C is run, it generates this code. I have done a bit of post-processing on the code to reduce the number of lines, thereby making it a bit easier to read in the video, but basically the gist is that it creates a state machine. It begins by reading 1 character. Using a switch case, it determines what to do based on that character. Say, if the letter was an I letter, it jumps to label YY26. At label YY26, it reads the next letter. If this letter is F, it jumps to label YY51, otherwise it jumps to label YY23. At label YY51, it reads the next letter. If this is an alphanumeric character, it jumps to label YY22. Otherwise, it returns the token if, because it has read I and F that are not followed by alphanumeric characters. At label YY22, it increments the reading position and continues to label YY23, which is also reached when the second letter was not F. At label YY23, if the character is alphanumeric, it jumps back to label YY23, otherwise it returns the identifier token. There is hardly any possible way that this scanner could be made faster even if you hand-wrote it from scratch. That is why I like RE2C. It turns the mechanical task of character-per-character matching into one where you can fully concentrate on expressing the desired outcome. This is what programming should be. And thus, we have completed the first step in creating the compiler, parsing the source code files into structures that can be processed by the code. Stay tuned for the next part in the series, where I implement a number of algorithms to optimize and simplify this code. Have a most pleasant and fulfilling day. Do zobaczenia. Massa Ulcheri. In the last episode we created a parser for a bee-like programming language. It parses each function into a tree structure where expressions contain expressions. Today we will focus on optimization. As I have said before, Much in programming is actually work towards making the work itself easier. The code I wrote so far does not single-mindedly just aim towards the end result. Code like this, for instance, helps constructing expressions using much shorter code than would be otherwise necessary. In that similar mindset, these functions I just added help identifying the type of the expression or the identifier. The topic of today's video, however, is optimization. In the interest of getting this video out in reasonable time, I'm going to compromise a little bit on good programming practices. I start by taking the list of functions out from the inside of the main program and moving it into a global variable. This will simplify the rest of the episode quite a bit. Much of the optimizations in today's episode concerned with replacing code with simpler alternatives that accomplish the same outcome. One of the most important factors that decide whether some code can be replaced with some other code is whether the code has side effects or not. A side effect is when an expression produces any other outcome than its return value. In this isPure function, we already wrote some basic rules in episode 1, but so far we assumed that any function call automatically taints the expression as impure. That is not necessarily the case. Calling a pure function, such as one that simply returns the sum of two variables, is a pure expression. For example, replacing two calls to the same function with one call, or deleting the call entirely, will not change how the program works, assuming the same result is calculated. We need a way to classify functions. This is more complicated than it sounds. The pure fcall cannot just make the decision when it is called. Instead, it will check a pre-calculated variable. There is a variable that indicates whether the function is pure, and another that tells whether we even know whether the function is pure or not. Of course, we need a way to calculate these variables. My language does not have any global variables, but it has pointers. If a function takes a pointer parameter and it dereferences a pointer on the left side of an assign operator, we can assume the function has side effects. It causes changes outside strictly its return value. Of course, the effect is commutative. No, viral. No, what's the term for that? If the function calls another function that has side effects, this function too will have side effects. Because the dependency chain between functions may run in any order, we must loop this resolving process until we no longer can find any new function to discern as certainly pure or impure. To implement this function right now, we needed a special kind of for loop that iterates through all sub-expressions in an expression tree. Here is how I defined the for all expr function. It operates on the depth-first principle. The first node to be processed will be the deepest possible child node.